Our final speaker for today's image acquisition technology session is Dr. Derek Peake, a professor of soil sciences at the College of Agriculture and Bioresources of University of Saskatchewan. Derek has over 20 years of experience using synchrotron-based techniques to investigate environmental processes. His primary focus of research is determining the reactions that decide the fate of toxicity of metals and nutrients in terrestrial ecosystems. So today, Derek will speak to us about development of synchrotron-based excitation-emission matrix spectroscopy for soil chemophenotyping.
Thanks. All right. Well, first of all, thanks to the organizers for giving me a chance to speak. And what I wanted to do today was shift gears a little bit because I'm a soil chemist, and most of the work that we're doing with Global Institute of Food Security, unsurprisingly, also involves soils. And while you can get really good contrast and really nice pictures of above-ground systems, the level of contrast and somewhat the attractiveness of images is inversely related to how much soil there is in the system if you're looking at roots and the microbiome and below ground. And so what we've been trying to do is come up with a reasonably high throughput method. Sure. What we've been working on is a reasonably high throughput method to look at what the chemistry of soils is in systems where there's a variation in plant phenotypes, so that root, microbe, mineral system. And we've been using synchrotron X-rays because, well, I'm a synchrotron guy, first of all, but then the other thing is that they're very flexible, and there's a lot of processes, physically and chemically, that happen when you interact materials with X-rays. The elemental composition you can learn via X-ray fluorescence, so you can do quantitative analysis. Chemical speciation in the form of elements you can learn with X-ray absorption, and mineralogy, crystallinity, and you can determine from X-ray diffraction. And because synchrotrons produce tunable X-rays, you can do all three of those measurements, but they're often typically done separately at different beam lines at different times in a fairly low throughput manner. And so what we've been working on is what if there were a better way where you could get all of the information, sort of the overall crude fingerprint of the chemistry of your samples in a short period of time. And we've done a lot of work at the SGM beamline at the CLS with soft X-rays, and they have solid-state detectors. We can measure the energy of emission as we excite through the system. And what we noticed was there's a very interesting property. Synchrotrons are good in terms of optics, but when you're exciting at 700 EV wavelength, then there's going to be some higher order light that's hitting your sample as well. And in fact, the third order of 3 times 700 is 2100. And so you can do a soft X-ray experiment where you think you're looking at iron, which is this, sorry, my thing isn't working very well. Anyway, if you look at that horizontal slice of iron, that's the measurement we were trying to make, but in fact there's some phosphorus fluorescence that's really well resolved on the emission line, and you can pull out a phosphorus K-edge spectrum that's actually 2100 to 2200 EV. And so in some ways, you're getting an extremely rich set of data by the fact that your fluorescence lines overlap. So if we take that and extend that to a really wide range, what we could do is just scan across an entire grading of the detector. And can you hit the video there? Oh, backwards. Hopefully it'll play. That's a real bummer. So if you go from 600 to 1200 EV on the horizontal axis there, what you actually scan through is you find places where Bragg's law is satisfied and you get X-ray scattering. You get the emission line, so quantitative analysis of the elements, and you also get chemical speciation of a wide variety of elements. And I'll just skip ahead since we don't have a video. And so what you see then is you can collect D-spacings, and you can get mineralogy, and you can get changes in the crystallinity of the samples from about 4 angstroms to about 18 angstroms, which turns out to overlap with almost all minerals that you find in soils. And then, if you take horizontal slices of this thing, then you can measure carbon, nitrogen, oxygen, iron, sodium, potassium, magnesium, aluminum, silicon, and phosphorus. It turns out those are almost all of the elements that we find interesting in soils as well. And so what this means is that you can simultaneously measure the chemical speciation of a lot of different elements. You could process them by themselves if you wanted to, but because this is an imaging-related grant and project, it's also possible to just treat these extremely data-rich systems as an image. And so at some level, this is what a picture of the chemistry of a soil looks like when interrogated with soft X-rays. So that's cool. However, I'll give you some little secrets of how the sausage is made, I guess. There's some problems with this. One of those is the data that I showed you took about 2 hours a sample to collect and is going to definitely radiation damage a lot of your soft X-ray materials. So you're not going to be able to look at carbon and nitrogen, which is one of the main elements we want to look at. These were proof of concept things, so we didn't have very good geometrical control, so our precision on diffraction was also limited. The other thing is that the flux in your sample and the fluorescence coming off of your sample is tremendously variable if you image across an entire grading of a SGM or a PGM. And what that means is at some levels you saturate your detectors and you get smearing, and if you back the detectors away and you narrow your flux, then you might get no counts at some of the elements, and so that's not good. And so we went back to the drawing board and revised our experimental system in the last year. And so our 2.0 version of this measurement is fast scanning or rapid scanning 100 EV steps across the entire 270 to 2000 EV region. And that takes about 10 minutes, but what it allows us to do is we can optimize the incoming X-ray intensity for each and every one of those 100 EV slices. And so you get a much more even, a much more higher quality EEMS image. We also have a computer-controlled hexapod. Oh, they were working again. And so we can precisely control the geometry of the system as well. And so here's a picture. We did a classical XRD experiment. Anytime you give a soil chemistry a research problem, they'll start working with Smectites, it turns out, where we either saturated it with magnesium and glycerol, so we would expand the clay, or we heated it up in the presence of potassium, so we would collapse the clay. And so you could actually see differences in the absorption line that's due to the presence of either sodium or potassium, not so interesting. But in addition to that, if you look at the colored lines, those are on axis with the X-ray scatter. And you could see that as you treated these samples, the intensity and also the position of the X-ray diffraction was changing. And that's totally consistent with a collapse from 14 angstroms to 10 angstroms in the presence of potassium and heat, and an expansion in the presence of glycerol. So we're able to do mineralogy, we're able to do X-ray diffraction on this kind of system. The other thing to look at is that these are nice, evenly spaced. There's not any super bright spots or super dark spots. Those are stitched together 20 different images. And it takes about, as I mentioned, about 10 minutes to do one of these samples. To pull out slices of the X-ray absorption, these are some of the same samples. Let's see if I go backwards here. If you look at the iron L-edge in the case of montmorillonite, which is the Smectite, the iron that's present tends to be in the iron 2+ oxidation state, and compare that to the iron L-edge of the nontronite, where it's iron 3 in the octahedral layer, and you can do those sorts of speciation analyses with a really rapid measurement. And so what I would say is we now finally have made this thing work well enough that we can get reasonable throughput. What I've done for I think they said I've been working in synchrotrons for 20 years. I've had 20 years of promising that we were going to understand samples that we really should have done at the very beginning, and doing it at the very end of projects, because it's so time-consuming and it's so laborious, and we only measure a few samples. But now, we can measure six samples an hour. That's a reasonable throughput, actually, and we can start to do this. We don't need to know what element that we should study in the beginning. We just measure them all, and then we can do multivariate stats. We can do cluster analysis, and we can figure out how to apply more sophisticated techniques in a more rational manner. And so we're continuing to do this. There's no beam right now, but as soon as it's back, then we're going to work on shifting from pulling out spectra and doing classical analysis into whole image analysis of these systems. So with that, I'll thank my research group who actually does all the work.